Hello everybody, thank you for joining us today. My colleague and I, this is Dennis Chung here, he's a materials engineer with us, and myself, Tony Tizzano, I'm a sales engineer for Eurotech. And today we're going to go over the advancements in liquid sealers for splices and terminals and some of the research we've been doing with that. So one of the main things with splices and ring terminals, especially as we begin to start packing more and more technology into these vehicles, we get more wires, and with that we increase the complexity of these to the point that we start to have issues with actually sealing it with the conventional sealing types. And with that we start to get moisture that comes into these wires. So in the top right hand there you can see a simple saltwater soak. At the start of the test you see the wire clean. Just 2 days in we actually start to see some corrosion on the end of that wire. And then 2 weeks we just see it completely corroded to the point of potential causes of failures in the splicing application, or in some cases actually getting that water into your electronics via the capillary effect, but not only that, but also due to the vacuum effect, which can be caused by the heating and cooling of electronics that aren't properly vented. Some of the conventional sealing methods, heat shrink tubing for one, which is obviously the most common one that we see in today's industry, have several issues that come with them. With splice construction, you start to see, if you don't have it properly constructed, you might see poke through the heat shrink tubing during the shrinking process, as heat shrink tubing is potentially much more fragile in its hot and shrinking state. Additionally, with inbound splices, you start to see the possibility of those heat shrink tubes sliding to one side and therefore exposing the copper and preventing an adequate seal. And then also with improper machine setup, you may see insufficient heating causing the heat shrink not to shrink enough, therefore not sealing the splice. Some other technologies out there to aid in the sealing of the more complex splices. We have heat shrink tubing, as we discussed, and then also additionally overmolding. With overmolding comes some other challenges, especially with certain wire types, different wire insulations that have lower surface energy are much harder to bond to, and therefore it may look sealed, yet the water is still able to get between the insulation and the overmolding. Another application we see is butyl rubbers. Sometimes with these butyl rubbers, they're petroleum-based products, and what can happen over the life of the vehicle is that petroleum-based product can actually go and pull the plasticizers out of your wire insulators. And with that, what can happen during some bend tests and things of that nature, the wire becomes brittle, and during those bend tests you actually get cracks and failures within the insulation itself. Another technology that we've seen more and more to try and seal these splices and ring terminals is solder. Now solder is not really designed to be a sealant, it's more to be something that is to prevent corrosion on your ring terminals or to help mechanical fixation of your splices. And as you can see in these bottom two photos, especially on the close-up there, you actually see damage to the wire insulator. So what happens is with that high temperature solder, it actually causes the insulator to expand and balloon rather than actually creating a seal in there. It will slow the penetration of water, but it most likely 9 times out of 10 will not stop it. So with the liquid sealing concept, the idea of this is to, rather than do an encapsulation like all those technologies that we saw before, minus the solder one, what we want to look at is actually wicking into each individual wire and creating a seal within each individual wire, rather than an encapsulation and relying on glue, for instance, or things of that nature to actually go and get around each individual wire lead, creating that seal. So as you can see in this microscopy photo here, a cross-section of a singular wire, within those little gaps in there you can actually see that a liquid sealant provides a seal in and around each and every strand, and as well as around and in the insulator as well. And with this, with the sealing with liquid sealants, what that allows us to do is, rather than have a complex construction, we can take some of those splices and ring terminals and combine those into one, therefore trying to simplify your construction rather than having multiple splices or ring terminals within the vehicle to help alleviate the chance of there being a failed seal. And at this point I'm going to turn it over to Dennis to talk a little bit more about the chemistry and technology behind it.
Thank you, Tony. Again, my name is Dennis Chung. I'm the material engineer at Eurotech. If you'll allow me to geek out a little bit and talk a little bit about chemistry and what happens inside the wire. So we did a lot of research looking at the details of the mechanism of how liquid sealant works inside the wire. So what I'm going to talk, the next few slides, what I'm going to talk about is what we know, which is our product Blue Seal. But yeah, this talk is about liquid sealant in general. So with that, I'll talk a little bit about the chemistry of our Blue Seal formula. So on the right, you have the basic componentry of what goes into this liquid sealant. Basically, we have the backbone of acrylate copolymer that's blended with some adhesive cyanoacrylate, blended with some flexible type cyanoacrylate. And that combination of additives, what happens is it has a combination of fast wicking performance, which means it's low viscosity liquid, which allows capillary force to really work well to wick into the wire. Also, there's some functionality that allows it to be cross-linked. When it's cross-linked, it gives it that heat stability as well as that elasticity that you need for it to be robust. So in comparison to some other products that are out there on the left, for example, ethyl cyanoacrylate system, in a nutshell, it's more brittle. As you can see on the bottom, the Blue Seal on the right, there's 1,300% elongation. It's very stretchy and soft versus a more brittle product on the left. And that elasticity is really, really critical to having a robust seal that can withstand bending and other mechanical stresses. So basically, this is an acrylic cross-linked alloy. So a couple of things, setting time, which is how quickly it sets or cures, and the strength of bond of this liquid sealant to copper as well as to the jacket. And two tests that we use to measure those are setting time test and adhesion strength test. So on the left-hand side, the setting time is tested by simply putting two copper blocks, square blocks together, sandwiching a 10 microliter droplet of sealant. So our block is 12.7 by 12.7 millimeter copper blocks, and we put a drop of sealant in between, put them together, and we time it. And after a certain amount of time, we lift it up and see if we can lift 2.6 kilogram of weight. And if it can hold that weight, that's the set time. And this product has a set time of 1 second. It sets pretty much immediately. And that's due to the combination of fast curing, as well as the fact that this is a very, very thin bond line. This bond line creates about a 60 micron thick bond line, and that's going to set pretty quick. Also, we call it setting time. That doesn't mean that it's cured 100%. As you can see on the bottom, the force required to lift a 2.6 kilogram of weight is about 0.16 megapascal, or 26 newtons. On the right-hand side, when we do an adhesion strength test, when it's fully cured and we put it in a tensile tester and pull, average tensile adhesion strength is about 115 kilogram force per square centimeter. So you can see that our setting time is established at around 0.1% of fully cured strength. But that set time is enough to give us a seal, a packing of the wire to give us a seal. A little bit about capillary action. That equation on the right here, that's basically the governing equation that determines how much the liquid is gonna wick in against the force of gravity. It's a combination of pore radius, the surface tension of the liquid, and the contact angle of the liquid against the solid. So the surface tension of the solid and the liquid creates that contact angle. The density, the G-force, those are other factors. Basically, we have all the numbers for this Blue Seal product, and we can measure that for other liquid sealant systems as well. The contact angle is 32 degrees. We have the surface tension value of 34 dynes, and when we plug it in, we get a certain a theoretical wicking distance, which I'm going to get to in a later slide. Another way that we estimate the depth of penetration inside of the wire is an empirical method. And by empirical method, what we did was we visually measured wicking height or wicking depth in a capillary glass of known diameter. So we got two capillaries of 200 microns and 500 micron diameter. And we allow the liquid sealant to wick in and measure the wicking distance. It came out at 48 millimeters and 23 millimeters respectively. And when we fit that into the power law equation that we saw in a previous slide, so that's the equation that we fit into, we get our coefficients. And using those coefficients, we calculate what a theoretical, empirical wicking distance should be in an 8-gauge wire. And when we plug in those constants, we get a theoretical wicking distance of 188 millimeters of wicking depth in an 8-gauge wire. Actually, that's not what happens in reality, because there are some assumptions that we make. So this 149 millimeter is a theoretical wicking distance based on that governing equation I showed earlier. That's for a pore size in an 8-gauge wire. However, there are some, real-world resistance to achieving that wicking distance. First, the fluid is non-Newtonian, so there's some viscous force or resistance to it. Also, at the same time, while the liquid is wicking in, it's curing at the same time, which means that the viscosity is increasing as it's wicking. So there's multiple dynamics happening at the same time. And also, you're forming a solid front on the copper surface, which means the pore diameter is changing as it's wicking. So all of these non-ideal factors factored in, your final wicking distance is somewhere down here, much lower than what ideal theoretical equation would predict. So here's a way we measure the actual depth of penetration. What we did was we get a wire, we strip the wire, and we put 2 or 3 drops of liquid sealant, Blue Seal, and let it wick in. And what we do is we cut the jacket. We cut the jacket in 2 millimeter increments, and we put it underwater, and we apply air bubble pressure. And we note at what distance from the tip does a bubble come out. So here you can see that bubble comes out right around there. And that table on the right shows the typical wicking depth. Well, actually, that cartoon on the right shows that some pores are going to wick in much deeper than others because of the pore diameter distribution. But the sealing performance depends on all of the pores being blocked. If you have one pore that's not sealed, then you're going to have a leakage. So the least common denominator depth of penetration is somewhere between 22 millimeters and 28 millimeters. So these are indicating where we stop having 10 wire samples out of 10 wire samples, 10 wire samples out of 10, achieving full sealing under 0.5 bars of air pressure. Next, I'll talk a little bit about curing. So curing of this sealant is initiated on the copper surface. This particular formulation is catalyzed anionic, which means a chain reaction occurs when a electron donor or alkaline molecule is present on the surface. Typically, what initiates the reaction is hydroxyl groups or OH groups anywhere on the surface of your adherent materials. And copper materials, you're always going to have a molecular layer of moisture or water in it. And in that moisture, you're going to have OH groups present. And whatever low concentration of OH there might be, it's enough to initiate a polymerization reaction. So the curing of this sealant initiates at the copper filament surface, and it grows and it progresses away, as you can see in the cartoon. And at the same time, viscosity of the liquid increases as that reaction front proceeds above the copper surface. So that's the image of what the curing looks like. It happens from the surface where you have moisture, which initiates the reaction. So we wanted to look at the cure rate. How quickly does it cure? How far and deep does it cure? And what we did was we used ATR, FTIR. FTIR is Fourier transfer infrared spectroscopy. So we put a drop of blue seal on our ATR, FTIR scope or probe window, and we just monitor the spectrum real time. So this cartoon shows how we laid out the experiment. What we did was we put some spacers, tape spacers on the window that controls the thickness of your liquid sample. And we put our copper block on top to initiate the cure, and then we measure the FTIR scan. So yeah, this chart shows the two primary peaks that we looked at to measure the rate of cure or degree of cure. One location is region 1 here. You can see that the peaks are pretty large, and the peak size doesn't shrink, but it shifts. It shifts because there is a CO bond in our chemistry that is affected, or the vibrational spectra of that CO bond shifts as it goes from liquid state to cured state. You can see shifting from here to here. And another signal for measuring the cure or the transition is the disappearance of the CC bond. So CC bond disappearing means that it's polymerizing. So this is an indication of polymerization. And in this case, the CC bond disappears. So you can see, it's hard to see there, but magnified, you can see that this peak is here and it disappears as it cures. So those are two ways we looked at to measure the cure rate. And another thing, there is a limitation to this ATR, FTIR probing technique, and that is the depth of penetration of the infrared beam is limited. Based on this equation, we're limited to viewing only the first 1 or 2 micron of the sample. So here is a diamond surface. Here's our blue seal liquid. The infrared, as it comes up through the diamond probe, it only sees that little sliver of the sealant. What happens up here can only be inferred by what we see down here. So that's a limitation that we have to work with, but we can do other techniques to get a fuller understanding of how the cure, the solidification profile advances with time. So here's a graph of cure time versus degree of cure. So if you look at the blue line here, so basically for a sample that's 50 microns thick, very thin sample, within a minute, it's fully cured. So it's basically a straight line curve. But as you go to thicker and thicker samples, we begin to see a profile going to the extreme of a 400 micron sample, up to about 20 minutes or so, it looks like it's not cured. But as you go to 200, 300, we begin to see a profile. So just from this, you can see that for a thin sample, you get very quick cure, almost instantaneous cure. But as you go to a thicker and thicker sample, it seems to take a long time. So there is a very quick exponential drop to this cure rate versus thickness. So what we did was we did a transposition of ATR, FTIR data. So we looked at data for different thickness film samples, 50 micron, 100 micron, 200 micron, and we simply transposed what we see in these thinner samples onto the thicker sample data. So with the 400 micron sample, although we can only see what's happening here, we can infer what might be happening here at the 200 millimeter depth by looking at this data and transposing it onto this sample, and for 150 millimeter and so forth. So we can get a composite picture of, for this thick sample, yeah, we can directly measure what's going on here, but we can also infer what is happening in deeper depths. So that's a simple and easy technique. And here's what it looks like when we put it all together. So you can see that on the left is degree of cure, and on the bottom, this time, it's distance or the thickness of the film. For a 50 micron film, yeah, it's pretty much 100% cured immediately. At 1 minute, it's 100% cured. But as you go to thicker and thicker samples, we see a profile being generated. So for this one, the thickest of samples, 400 micron samples, yeah, it takes 480 minutes. Yeah, it seems extremely long time to fully cure, but that's what the profile looks like. So in summary, the cure profile is very exponential decay of cure rate. And there's a reason for that, related to chemistry and the stabilizer package that we put in there. And speaking of stabilizer, we looked at the shelf life stability. So this is a very quick curing chemistry. Is it going to cure quickly when it's sitting on the shelf? Well, there's some stabilization package that's put in there that guarantees that it'll be shelf stable for up to 6, 9, 12 months of shelf storage. And we look at tensile strength to copper, and also change in viscosity, as well as a set time. And you can see that the tensile strength remains pretty stable within spec. Also, the viscosity is a measure of, is it curing, is it polymerizing in the bottle? It is doing a little bit, but it's staying well below our control limits. Same for set time. A little bit of microscopy to share with you. This is what it looks like when we put it under a microscope. So we cut a cross-section of the wire that's been treated with blue seal. We polish it down, put it under the microscope, and you can see that all the pores are fully packed. And if we zoom in, that's what blue seal looks like. Very pretty, in my opinion, and fully packed. We did some sealing durability performance test to the gamut of typical OEM requirement. Air bubble pressure up to 0.5 bars. That's pretty much a standard. We exposed the sealant treated wire to chemicals, short-term heat aging to extreme temperatures, impact resistance, vibration, environmental cycling, hot and cold of different humidities, flexibility. We bend it, applying mechanical stress to it. It withstands all of those durability requirements. Little note on 300,000 hours of heat aging at 125 Celsius. So this is one of a popular OEM requirement. Here's an actual sample that we heat aged for 3,000 hours. And here's a cartoon of a wire. And this is the location of this microscope image. So this is right at the tip where we apply the blue seal. And you can see that, there is some heat damage because you can see some channels developing, some opening between blue seal and the copper. That's because, there is some heat-generated volatiles, and the volatiles have to escape. And that's where these volatile channels are visible under a microscope. So when we take another picture at a deeper depth, so we go to 20 millimeter depth of a 3,000 hour aged sample, we can see that the pores are all obstructed. It's fully packed and it's sealed. It seals. And when we go to 40 millimeters, same thing. It looks like it's undamaged, fully packed. And as you go to 60 millimeter, now we're starting to see, again, those pores or those channels appearing again. And it seems that we've hit the other end of the blue seal front, where the volatiles that are created by heat is escaping down the other end. So that's what we're seeing. But through most of the bulk of the wire tip, it looks like it's pretty well packed out. So this is just a schematic of what we observe through the microscope. There's some heat damage after 3,000 hours at the tip, and at the front of the sealant, we see some heat damage. But for the most part, it's still fully packed and it's still sealing. So that's what we see, and I'll let Tony take it home from here.
Thank you, Dennis. Okay.
So did you use the same amount of blue seal to get the 60 mm quick depth?
Could you repeat that, sorry?
Did you use the same amount of blue seal that you stated previously when you're showing what's the actual amount of quick depth you achieve? Like a roll?
Yeah.
In order to perform this test after heat aging as well?
Yes. So the question is the amount of blue seal from the beginning of the test same as the amount of blue seal at the end?
I think you were
Oh, we show like around 22 millimeters, and now we're showing 60. Yeah. So yeah, good question. So 22 millimeter depth was achieved when we put 2 or 3 drops. So these samples were dipped. So we let it just soak as much as it wants to go. So it ended up achieving somewhere between 40 to 60 millimeters of penetration depth.
Is there a recommendation on how much blue seal to use?
So the question was, is that the recommendation of how much blue seal to use? You want to take this?
Yeah, so for that, we actually have a calc sheet that we've developed as well with the various wire cross sections and things of that nature to achieve that 25 millimeter depth of penetration for the application, as that's what we did all of our data validation testing too. So given all this technology and the study of this liquid sealant, yeah, we've developed and seen how we can make this work within the wires, but now we need to actually bring it to market and show how we can apply that to our splices and ring terminals, as it needs to be somewhat of a precise application, because you want, especially for ring terminals, you don't want to get the material on the mating surface, but you also want to make sure you get the material where it needs to go to properly and adequately seal your splices and ring terminals. So starting out with a splice application, it's a little less need of precision as a ring terminal, as it's eventually just going to be covered by a splice tape or a heat shrink tubing for that matter. So ideally you want to take your splice and you want to fully submerge it into a bath of this liquid sealant for 2 to 10 seconds depending on splice complexity. Our calculation sheet can also guide you in that direction on how long you need to actually dip these splices. And we also have a geometry of a bath such that we try to reduce the amount of the splice that's actually in the material, but rather we just want to make sure that the copper or the exposed strands are fully submerged. During this application, the blue seal wicks into the wires, and then at the end of the application you want to tap off any of the excess that may be on the outside. And this is in maybe a lower volume application. In some of our higher volume applications we've developed equipment, which you'll see here momentarily, where we actually can blow off that excess material. On the flip side with ring terminals, we look at more of a precision dripping application. As I mentioned earlier, we want to prevent getting the blue seal or any liquid sealant for that matter on the actual mating surface of the ring terminal. Our actual target is the strands between the insulator and the nugget, or the sonic weld, whatever it may be. That's where we want to apply blue seal and allow it to wick into each individual wire strand. And then in some cases we also actually will apply to the tip of the nugget or the sonic weld, and the reason being for this is we also want to ensure that any porosities or cavities that might be within that nugget also get sealed, because surface corrosion on a sonic weld or mechanical fixation isn't what causes that splice to fail. What happens is if you get internal corrosion and it starts to swell and expand, you can actually cause your sonic welds or your mechanical crimps to expand, and then therefore causing failures in that matter. So we want to make sure that in all cases we have any porosities fully sealed with that material. And then another tip with this is with eyelets is making sure that you have them tilted so that the wires are at a lower angle than the mating surface, and that just helps to prevent blue seal from traveling or any liquid sealant onto that mating surface. So some low volume equipment, like where we started out, we made some simple HDPE baths where we're dipping the splices. And then in addition to that, for ring terminals, there's some hand application systems for applying with needles. A company that we work with is Nordson for that, where they supply various different pumps and precision drip systems that allow us to apply that liquid sealant in the manner that we would like. Looking more towards a higher volume application, for splices, for instance, you can see this system here that we developed, providing operational feedback, a status light. Essentially what it's doing is you'll program in your dip times, things of that nature, as well as the depth of the bath that you need to ensure that that splice is fully dipped. And with that, during the application, the operator's dipping the splice, they can the machine will give them feedback as to when they've dipped it long enough, or if they pull the splice out earlier, we're also able to detect that and tell the operator that it's not necessarily a bad part, but you need to resubmerge that sample to ensure that it gets the adequate amount of material to seal. And another aspect of this that I talked about, getting the excess material off the splice, you can see in the front here we have the BOS, which is the blow-off system. Essentially what that does is it has two air knives that when you submerge it into that bath, it's actually going to blow off any excess material. And we use a downdraft ventilation system to draw out any fumes that there may be. And then in addition to that, we also want to look at performance monitoring. So as I mentioned, the full insertion detection, as well as having counters for okay and not okay parts for every given shift. And then the dripping application, as I mentioned, is a little bit more precise. So we have, and for higher volume production, we want to have, make sure that the operator has the least amount of downtime as possible when applying this material. So we have dual feeder racks, so while one tooling is being applied to, the other one is able to be loaded and unloaded during that application, as well as auto cycle starts, so that as soon as it gets inserted, it starts running. And then with that, we also make it very easy to program and dial in where you need to apply that material so that you have good replication, repeatable solution for every terminal that is applied to, with also live step-by-step automations within that screen. And then the tooling and fixtures for holding those various terminals are relatively low cost and easy to swap out, in addition with having even a barcode scanner for that matter to quickly swap between different configurations. And then this next, I'm going to play a video here just so you can see this equipment running and in action. So this is the, we call it our BPDM. So you'll see it applying, don't need the audio, sorry. You'll see it applying to the ring terminal in the specified areas that that I showed you earlier, as well as at the tip of that ring terminal to ensure that it is fully sealing those porosities. But yeah, so then during that application, as you started to see when it switched back over to the other angle, the operator is loading the other tooling, therefore having little to no downtime in helping increase the cycle count. That is the end of our presentation. Thank you for your time. If there's any other questions, we'll be happy to answer those now.
Of distance between individual strands, but probably slightly larger gaps.
So with larger gaps, are you saying like in between individual wire leads?
In wire insulation.
So the question was whether or not you're able to use this material in between actual wire strands or wire leads rather than just the strands themselves. This specific technology is more designed for the smaller gap applications. That's what we developed it to. There's various technologies for those larger gaps, as well as like some silicone sealants, as well as I mentioned, butyl rubber or mastics. That would be more in that realm. Again, you still run into that complexity of having to make sure that material gets everywhere it needs to be, similar with heat shrink glue and the complexities with that. Whereas we're taking a different approach, working to make with something that's more repeatable and doesn't have all those limitations. So, yep. Go ahead.
What's the smallest wire you deal with? Because you're showing everything is large. What about down in 20, 22 gauge wire?
Yeah, so we've done testing. Our calc sheet, we have wires in there everywhere from like a 0.22 millimeter squared all the way up till like we work with 8 to 10 millimeter square cables. With no issues in sealing that. It's surprisingly enough, across all those different wire configurations, you'll see it almost to some extent maintains the same gaps within those strands, because as you get to the smaller ones, you have less strands within them, and as you get larger, you have more strands, and it tends to fall in the same realm and have the same average gap size throughout those various wires.
The general automotive specs require flame retardancy and abrasion resistance. Did you test it according to this requirement?
Yeah, so what we did with our, so the question was, did we test the full gamut of testing with all the OEM specifications for flammability and abrasion? Liquid sealants, since they are inside the wire, it's kind of like, it's a little bit obscure of how to test it. But what we did is we based it off of like what the OEM validation testing you would go through for heat shrink tubing, for instance. So we looked at all the major OEMs, picked some of the most challenging tests with that, and went ahead and actually ran that full gamut of testing, flammability, and everything of those likes. But again, at that point, since it is an internal seal, like some things like abrasion and things of that nature, obviously you're testing more of the wire than you are the actual seal, since it's an internal seal. Good. All right, we'll go with you first.
Did you test the effect of the sealing after it's seen like high voltage, for instance? Like if 1600 volts or so were put on an assembly afterwards, is the steel still intact at that point?
So the question was, if we apply a high voltage to it for an extended period of time, does it maintain the seal? That isn't something that we've directly looked at. We've had some partners of ours and stuff do testing where they are applying to high voltage cables or connectors for that matter. And during that testing, they did maintain the seals. We haven't specifically done, like, set up test standards for that to look at that information, but it's something that would be interesting to look at in the future.
Just a quick question, with the short shelf life, do you have any problems with distribution? Because at 6 months shelf life, by the time I get it, I may not have any life left in the product if it's in distribution, or how are you addressing that?
So in regards to the shelf life, we have a very short lead time on the product. A lot of it's manufactured to order, and then with forecasting, we're able to really alleviate a lot of that. In addition to that, some other things you can do. We send the material in a foilized pouch, sealed pouch, so it prevents any moisture from getting to it or UV exposure. But in addition to that, another thing you can do is store it in a refrigerated system anywhere from 5 to 10 degrees Celsius to help prolong and maintain those initial properties of the product. But overall, I think with the current supply chain that we've set up, I don't think it's too much of an issue, especially because we don't have super high MOQs, so it allows you to do more frequent ordering to keep that material fresh, especially if you follow a FIFO system.
Would using this on a standard TXL, GXL wire on both ends, would that be an acceptable substitute for like anti-capillary wire, where I could just buy a normal wire and use this on the ends instead of specifying a whole new wire type?
Yeah, so instead of using anti-capillary and using a liquid sealant on either end, yes, that is definitely something that you can do as an alternative. The one thing you need to make sure is that this material is applied after you create your terminations. Because I know with anti-capillary wire, a lot of times you have to clean it prior to doing your terminations, because obviously with sonic welding, if you have foreign materials in there and it's not clean copper or aluminum, you're going to run into the issues of having inadequate welding. So yes, it can be an alternative for anti-cap wire. We've done a lot of testing with that because it's stopping the wire or the water at the entry point.
Okay, thank you.
Does it have any impact on wire resistance?
So does it have any impact on wire resistance? From the testing that we've done, we haven't seen any impact on the wire resistance, mainly because, so with this technology, since we're applying it after the fact of the termination, so that bond of the conductor has already been made, and the material is not going to get where that bond's already been had or already been created. So with that, in theory, it shouldn't affect the resistance. We haven't tested it in depth, though. Requires some very expensive testing equipment. I think they call it the gold ball test, if I remember correctly, which a few tier ones have out there. All right, well, with that, I'd like to thank all of you for your time, and I look forward to seeing you.
Yeah, if you have any further questions, you can come up to our booth, booth number 615, and we'd love to get into the weeds of this product.
Thank you.
Yeah.